Howdy Calc BC, welcome back. Today we're going to talk about section 7.6, which is integration by tables. And so what you may not realize, or maybe you figured out by now, is that all the integrals that we're doing, or that we have in our book, have been done before. And a lot of integrals that we haven't seen yet have been done before. And mathematicians, as I like to say, we're sort of fundamentally kind of lazy people. We don't write words, we write symbols, and we shorten everything up. And we also like to keep notes. And so pretty quickly it became pretty evident to folks who were working in calculus that kind of the same thing happens over and over again with integration. And so what we did was we put together a book or a table of integrals. You'll find this on page A27 in the appendix of your textbook. There's a whole lot of different integration formulas in there. And so when you're doing an integral, what you might try is looking to see if that integral matches the basic form of one of the integrals in the table. Sometimes it's not an exact match. Sometimes the integration formula yields another integration formula as you go through, as we'll see here in a minute. And then there's a couple of special substitutions that Dr. Larson is suggesting in here for certain situations. And we'll take a look at what those look like here as well. So without further ado, let's jump in. Grab your book. Definitely get open to page 524 for the section, but also maybe put a pencil or something in the back there on page 827, because we're going to flip them back and forth between those pretty regularly. So when we are looking at integration using tables, as you probably have noticed if you're in the book on page A27, they're numbered in our book. They're numbered in the actual book of integrals as well. And so this is a small selection of the ones that we actually have available, but there's, I'm just trying to remember, 91 different integration formulas in here. And so what we'll do here is we'll take a look at a couple of examples that, sure, yeah, we could do them by some other way. But, you know, now that we have the tables available, maybe we just look them up on the table. So my first one here is the integral of, there we go, dx over x times the square root of x minus 1. And when you first look at that one, you know, my initial thought is, oh, is it maybe an arcsecant, right? Because the x is outside of the radical. But unfortunately, arcsecant would require the radical to be x squared minus 1. So it doesn't quite fit. And so we could, you know, we could try u substitution for x minus 1, get x in terms of u. We could fiddle around with that for a little bit. Not really a partial fraction decomposition because of the radical in the denominator. So, you know, you'd probably be looking at integration by parts or something like that. Well, what I want you to do is look in the back on page A27. Oh, sorry, that's where the table starts. It's actually page A28. And we're looking at integration table, the formula for number 17. And my phone's making some noises over there. Sorry about that. So with number 17, you can see that that's the pattern for when you have 1 over u radical a plus b u du. And they give you two choices, one for a being positive and one for a being negative. And in this case, you know, we have a negative a because we have -1 for a. B in this case is 1 right here, right? And so we can just go down to the a less than 0 version of that formula and kind of plug in. We know we have a is 1, sorry, a is -1, b is 1, and u is x. And so when you look at the a is less than 0 formula, you see you get this integral equals 2 over -a arctan radical a plus bu over -a. And of course, there's a plus c. So all we have to do then is plug and play basically into our formula here. So 2 over negative a arctan of radical x minus 1 over negative a, which is 1, plus c. And so you can see pretty quickly we get 2 arctan of the square root of x minus 1 plus c. And there we go. Nice, straightforward. Now that we see it, you know, we realize it's an arctan function, you know, you could probably imagine how they did a squared minus u squared kind of thing in our integral there. But you know, without having to do all that, we can just look it up in the back. Integration by tables is an important technique in that. I had a physics professor, and he said, look, we do all these things one time so that you have them in your notes, and then from then on, you know where to look them up. Calculus isn't quite like that, but it's close. Once you've been through Calc PC, you know, you'll have your notes, you'll have your notebook, and don't throw it away, because as you go further up the math chain, these techniques and things become very important, and we rely pretty heavily on them as we go through. So as you work through these problems, you're going to notice that yeah, the integration by table is pretty handy. Of course, when we go to do some sort of an assessment on this stuff, sometimes people were always bummed because we couldn't just use the table the entire time. Obviously, you know, in this environment, I'm going to ask you not to use the table, and some of the equations might be a little tougher to integrate because of that. But hopefully the correct technique will come out pretty straightforward. So I'm not going to work through examples 2 and 3. I think those are pretty straightforward for you in there. I wanted to jump ahead to the reduction formulas and then the special substitution for sines and cosines, because when we have those integrals that don't quite match up, you know, it'll be interesting to see how you put them together. So I've got the integral here, square root of 3 minus 5x over 2x dx. And so what I mean by a reduction formula is, if you look at formula 19, okay, so go back into there on formula 19, you'll see that this is number 19. You'll see that it says the integral of the root of a plus b u over u du. How that is, my green screen is failing me there. So that is equal to another integral. So it reduces the integral down. It's 2 radical a plus bu plus a times the integral of du over u radical a plus bu. And you probably recognize this one right here, right? Isn't that the one we just used, right? Number 17. So 19 is a reduction formula. It takes the complicated integral, radical of 3 minus 5x over 2x dx, and says, well, you know, that's actually a form that can be reduced, so that then you can apply formula 17. So there's lots of them in there. If you're looking there on what is that, A28, that result in a new integral as part of your solution that then hopefully fits one of the previous integration formulas. So the reduction formulas allow you to take, it's basically like an integration by parts that's built in, and in the parts thing, you get the u times v, which is here, and then you get the v du, which is over here, and that's basically what this is. So for us, right, the first of all, the 1/2 needs to come out. So we can even use this formula. Okay, so now you can see I've got a is 3, b is -5, and u is x. So this will be 1/2 times. So now it's 2 root a plus bu. So that's our 3 minus 5x. Okay, plus a, which in this case is 3. And then the integral of dx over u x radical 3 minus 5x, like so. And now with that integral of dx over x root 3 minus 5x, if you go back to formula 17 right here, now actually we need the other version of formula 17, don't we? We did a is less than 0 last time. This is the one now when a is greater than 0. But you get the idea that we're going to get root 3 minus 5x plus 3/2 times. Now I'm just going to go back to 17 in the back and take a look for a greater than 0, and I get 1 over where I lost my place. There it is. 1 over the square root of a natural log square root of 3 minus 5x minus square root of 3 square root of 3 minus 5x plus the square root of 3 plus c. And there we go. And I think we all agree that's kind of a messy looking integral. So yeah, this really simplifies some of the more complicated ones. So that's what a reduction formula is, though. That's how it works. The last thing, there's a blue box on page 527. And I think it's important to recognize that there are going to be, when we have rational functions of sines and cosines, there's going to be some substitutions that you're going to want to make in order to get it to look like one of the formulas that's in the appendix there, starting on 827. And so I won't I'll spare you me doing the proof. I just let you know that a lot of times the substitution that we want is that u is going to be sine of x over 1 plus cosine x, okay, which is equal to the tangent of x over 2, okay. And what that ends up doing is it gives you a couple of options. Cosine of x then, through a little bit of solving here, turns out to be 1 minus u squared over 1 plus u squared. Sine of x turns out to be 2u over 1 plus u squared. And then dx turns out to be 2 du over 1 plus u squared. And a lot of times that substitution is what you need to help your integral fit one of the patterns from the back of the in the appendix. So really important substitution when we have that rational function of sines and cosines. And it's not one that we could do with the powers that we did before. So with the powers that we did before, right, if it's, if you can, you save a cosine, sub out all the sines. That way, du is just cosine x dx. But this is one that's not really feasible. And you're thinking, oh boy, if you take a look at example 6 in the book, that sort of substitution wouldn't work. The argument of the two functions is actually different. So there's already some issues that arise with that one. So anyway, I'll let you peruse example 6 at your convenience to check that out. And the application of this particular substitution is what allows us to do example 6 using the table of integrals in the back of the book. All right, so not a technique that we would necessarily have directly on a test, but it is certainly a very useful technique using the table of integrals to integrate. It's it's a darn good way to come up with an integral. So that's it for today, guys. Thanks so much for checking out the video. I'll see you guys in class on Monday, and have a great weekend.